Okay, well, good morning, good afternoon, or good evening, people of the future that might be watching this. For as long as the ASHRAE handbook has existed, mechanical engineers have been doing load calculations. We do cooling load calculations, heating load calculations, and then more recently, in the last 30 years, annual energy calculations. Unfortunately, in the US, it is not common practice to validate those calculations. Most of the time that an engineer does a peak cooling calculation for a building, it gets built and then put into service, and there's no real concerted numeric effort to go back and check those calculations against the peaks that actually occurred in the building. And that's similar for heating loads and in most cases for energy calculations as well. Since there's no regular checking process, inaccuracies probably shouldn't be surprising to most of us, but they are uncomfortable nevertheless. In the last grip of years at Kaiser here, we've been doing some of this checking. We started checking energy use against the energy models about 8 years ago, and we've just consistently found a broad level of inaccuracy in just a number of categories. More recently, in the last few years, we've come into some tools and some data sets that really allow us to look at the loads that occur in the buildings, sort of historical load for each hour of the past year or past years. And so today we're going to be talking about that data and quite heavily about cooling loads. My personal premise or theory in all this is that our industry calculation tools are sound and valid. I don't think we should throw away load calculations or energy modeling tools. Rather, the accuracy problem that we have is a problem of garbage in, garbage out. And so under that premise, the task at hand is to find the set of inputs that yield a more accurate set of outputs. Last week, we had another team looking at patient rooms and operating rooms and some other spaces in the hospitals in terms of what those inputs might look like. And then today, we'll be talking about clinics, which is great. It's a tremendous portion of our work. So with that, I'll turn it over to Jessica. Take it away.
Thank you. Yeah, and the Smith Group team just wants to thank the Kaiser team and welcome you to our final presentation of this data analytics project, where we did look at the medical office buildings and develop that energy model based on design assumptions. Before we get into the presentation, we just want to introduce ourselves. So Jessica Vines, mechanical engineer in the Boston office, and I helped with mechanical support. I will then have Harshana. How about you go next?
Hi, my name is Harshana. I'm also from Smith Group. I'm part of the building performance group. Ting and myself worked on the energy analysis portion for this project. Ting, you want to go next?
Yep. Hi, this is Ting, energy modeler from Smith Group performance teams as well, and working in the Phoenix office currently. Next, Peter.
Hello, my name is Peter McNally. I'm a data scientist at Smith Group, working in the technology and practice team in our Ann Arbor office. Eli?
Hey everyone, my name is Eli Cowart. I'm a data analyst in the Washington, D.C. office. I work very closely with Peter, also part of our technology and practice group.
Great, so there's our team. Next, just what we're going to go through in this presentation. We'll start with our background and motivation, look at our actual load calculation methodology at both the zone and facility level, preliminary actual analysis of BMS data, and then look at our energy modeling, our assumptions, recommendations, QA/QC, and our case study zone level analysis, as well as finishing off with our next steps and conclusions. So for some background, back in 2021, the Smith Group started to look at peak cooling loads for acute care facilities, and this was part of the Kaiser templating project. So we started off because the fact that Travis mentioned, a lot of the time our design calculations don't really line up with the actual, so we wanted to look at that and find diversities. So we started looking at those actual peak cooling loads. And this violin plot shows some of the thinner pieces here show the lower frequencies, the median shown by the line in the middle, and then the thicker parts show the higher frequencies. What this graph shows is that, or the violin plot shows, is that medians are actually fairly consistent across the zone types, but it's the peaks that you have higher discrepancies between them. Then next, we looked at the aggregate max block cooling sensible load. And it's a caveat that it's not the true block sensible cooling load because we didn't group the spaces of the different types onto the zone. Instead, we looked at the highest coincident peak of X number of zones of a specific space type, and that became our block load. And we normalized it by area and hour. So here, the block loads on the y-axis, zone counts on the x. And if we start on the left, we see at the lower zone counts, that's where you really want your design load is likely what you design around. But as you get to higher counts of zones, then you have a drop off as far as the block cooling load. So we want to find a diversity factor that could help our designers in the future. We did not have the actual design peak cooling loads for these spaces. So what we did is we used our actual data and the 0.4% exceedance value. And that meant that 99.6% of all the data fell within that range. And that's how we calculate our diversity value. And similarly with the zone count, as you see, you have lower number of zones, you're closer to the value, but as you drop off to higher zones, you can see diversity values as low as around 40%. And as designers, we'll use around 80% diversity. So that's a pretty big gap. This resulted in an ASHRAE paper and our favorite table number 2, which you'll see a little bit later in this presentation as well. This has diversity by zone type for the acute care facilities, which will be helpful for designers to use. But at the end of the study, we felt like there was just something missing. We had more we wanted to do. So we would love to have looked at different climate zones, more facilities, but also one of the big things was looking at the air handling unit and system facility level, which really leads us to where we are today with our current study. And the reason why we want to look at that facility level is that our energy models will often overestimate the load, but underestimate the energy usage. And the Kaiser basis of design document doesn't have any diversity factors that allows for us to close that gap between what actually is happening at the facility and then what we're seeing in our design calculations, whether it's load or energy level. And to that graph right there is showing the cooling load profile and the basis of design. And ideally, our energy models and actual data would match that, which they currently don't. So that's what we were trying to aim for throughout this study. For our process to get there, we wanted to look at around 7 to 8 facilities, but then we quickly whittled that down to around 3 and then came down to 1. That was a result of some missing data and just time to complete the study. But Peter will talk a little bit later about how we got to that process. One thing to note is that the Hesperia is served by a DX rooftop unit with VAV and electric reheat. This is important to note because like the last study, we would love to do more. We'd love to look at other facilities of the same type, other facilities in different climate zones, and then also different system types. We always like to start kind of with the end in mind. So I'm going to share some of the results that we found, and the rest of the team will dig into the details of how we got there. So to the left is the yearly actual cooling data. And then to the right is our energy model built off the basis of design assumptions. As you can see, the red line is the peak from the actual data, and the energy model blue lines extend above that. So to start to close the gap, what we did is we started with that basis of design model, which we will refer to as 100% diversity throughout this presentation. And then we stepped the diversity down by 10% from 90 to 50%. What we found at the system and facility level is that applying a 50% diversity factor got us closer to the energy model peak sensible cooling loads matching the actual. Having said that, we wouldn't recommend that you do your equipment sizing on the 50%. We'd rather you do your sizing based on 60 to 70 because as engineers, we love our safety factors. And that safety factor will allow for future growth and also environmental changes. So I'll hand it off to Peter to start to dig into how we got to those results.
Great, thanks, Jessica. I'm going to take a step back and talk about the methodology for those actual load calculations. So I'll talk about the data collection as well as some of the calculations. Looking at the next slide. This slide really outlays at a high level the data processing. So starting on the left side there, we have three different sources. One of them is the HVAC data, which is exposed via the Clockworks API. And there's two kind of key components that we got from there. One is the outside air temp that's collected at 5-minute intervals. It wasn't perfect, so we did have to augment that with some other sources, and that's discussed a little bit in the appendix. And then the other one is the equipment points. So both for the air handlers as well as the zone equipment, we were able to get that data directly from the Clockworks API, which was really helpful. In addition to that, there are zone attributes that the Kaiser staff collected and gave to us in Excel files, as well as equipment plans that we were able to look at. We stored most of the data in our Databricks repository, and that's where we kind of brought everything together and enabled us to do the calculations. We also use Microsoft Teams to transfer data between Kaiser and Smith Group. And then finally, we use Python, both within Databricks and outside, to do analysis as well as create data visualizations. And we also use Power BI. Moving on to the next slide. This shows in more detail the Clockworks Analytics API, and that diagram is taken directly from their documentation. So using this, we were able to select the equipment classes that we wanted, the zones and the AHUs, and then also select the buildings to ultimately get to those individual points, and finally to that raw data, which is the basis for all of our actual load calculations. So moving on to the next slide, this is a little more in-depth of the process of that manipulation step. So we have the zone attribute data, which we read from the CSV files into Databricks, and we made sure all the data was consistent and created a lookup table that we look at later in the process. But before we do that, we get the sensor data, and we get that using that Clockworks API, progress down through the API hierarchy that I previously showed to get the zones and the points, and then loop over each day and issue a request for each of the needed points for each pieces of equipment. Once we get that, we join that equipment data to get the zone name. We pivot that data a little bit to make it more applicable for analytics, and then we augment it with additional date and time columns. And then finally, we bring everything together, add the attributes for zone type and area, aggregate it, and then calculate our loads. The next slide shows an example of what some of that raw data looks like. So again, this is 5-minute interval data, which you can see at the timestamps. And then in the sensible cooling load, it shows the 3 fields that we use, and those are indicated with the point type names. So we have the room air temp, supply air flow that we use. Then here, this is just a little bit to talk about the different levels that we calculated load for. So again, we have 8 facilities at the zone level, 6 of them in California, 1 in Maryland, 1 in Hawaii. It's a total of 1,100 zones. There's 3,000 distinct VMS points that we collected. And in total, from those API calls, there's almost 300 million total data points. Just to the right, there's an example of some of the visualizations that you'll see in this presentation that were derived from these points. Moving down to the facility level, again, we just looked at the air handling unit for this, and part of that was due to that VAV box with the electrical reheat. We didn't want any of that influencing the facility level load calculation, so we used the 3 air handling units for Hesperia. That's 9 distinct VMS points, and even that is still almost 1 million total data points. And again, to the right, you'll see some of the visualizations in this presentation that were used for that. I will note just to the right there, there's kind of an intermediate level. Those are the 3 MOBs that had sufficient zone attribute data that we were able to get from those mechanical plans, as well as the other data in the CSV files. And Eli will talk a bit about that later on. And then this slide is just kind of an abstract level. It shows how we calculated the sensible cooling load and each of the different factors that went into that, both at the system level and the zone level. Again, the outside air temp that we used, the return air temp, supply air temp, and then the supply CFM. So here's some of the initial load analysis that we found at the zone level. I guess these were very kind of interesting maps to look at. We call them cooling intensity maps. And this shows a relative comparison. These are 3 of the facilities that we looked at. We have the additional ones in the appendix as well. Just kind of looking at it at a high level, you kind of see some different patterns. On the left, for example, Berkeley doesn't have any or very little cooling that occurs outside of the normal business hours. Hesperia shows kind of a similar relative intensity, but there's definitely cooling that happens throughout the day. And then Irwindale really looks different from the other 3 or the other 2 in that peak cooling loads occur in the early morning hours. So again, focusing on that center one, Hesperia, that's another reason that we use that to compare to the energy model. And then this slide is the same as the previous one in terms of data. It's just a little more granular. So along the x-axis is the day of the year as opposed to the month of the year, and then the hour of the day. So all 8,760 hours of cooling load. And again, the rest of these are in the appendix as well for the other 7 facilities.
So as Justin Travis alluded to at the beginning, one of our main issues is comparing the basis of design cooling loads to our actual data. And so we can see here, based on the basis of design that Kaiser gave us at the start of the project, we kind of recreated that with our actual data using the same style of chart. And so here's that chart for both Berkeley and Hesperia, and you can see the green line is the maximum values that either of those medical office buildings saw throughout the year, as well as a couple different intervals, minimum to 20th percentile, 20th to average, average to 80th. That those hospitals saw, and overlaid on top of both of those, and especially during the middle of the day during office hours, we can see way higher with that dashed red line is the maximum that the BOD predicted. And you can see, especially with Berkeley not having very much cooling during off hours, there's virtually no time at all where the actual data ends up being higher than what the BOD predicted. So next we're going to turn it over to Harshana, and she can show us how we're going to try to remedy that with our energy model.
Right. Thanks, Eli. I'll be talking about the energy modeling assumptions and the lessons learned as we went along. So first, I want to talk about, do you see my screen, right? Progressing. Okay, awesome. I'll be talking about the methodology. So we did the energy analysis using IESVE. The actual geometry was based on the Hesperia floor plans, and envelope, plug loads, lighting, people, all the internal gains are basically taken from BOD that was provided. There was some discrepancies between the BOD and the assumptions we made, but we will be talking about that in the next few slides. The outside air is based on Tile 24, California Tile 24. So we used weather file to start with. We used a closest TMY3 weather data that was close to Hesperia, and we used that for the analysis. Once the system load calculations were done, the cooling load profile was compared from the energy modeling cooling load profile was compared to the actual BMS data. So we learned a couple of things as we worked on the methodology. So since this was an existing building, the BOD existed, and also there was data to compare with. But for energy modelers who are starting a new project, we recommend to start from a previous similar project. If it's a hospital building, use a hospital building which was recently built to use the data. That would give us the best steps to start with. That way, you can fine tune the model to be as accurately as it would perform. Secondly, so we had measured outside air temperature and the dew point temperature on site, which we used to fine tune the model after the model was built, and that actually helped us to align the energy model very close to the BMS data. If it is not available, we would recommend to use California weather files. They also, the NOAA or the Weather Underground, they also have the previous year data, which is more recent than using TMY3 because it's a statistically averaged weather data. So that also helped us, I would say, to fine tune the model to be closer to the BMS data. Lastly, we used one schedule for plug loads, lighting, and people. This was for the sake of simplicity, and also it was we recommend it because it's easier to edit and make any additional changes in the future if you want to have one simple or two schedules. Ting will talk about the schedules in the next few slides. So other general assumptions and omissions we made. So assumptions, like I discussed before, envelope, lighting, plug loads were all from the BOD. So the glazing term, the BOD provided center of glass value, so we had to make an assumptions on the assembly thermal performance for the glazing. Apart from that, all the walls, roof, thermal performance data was taken from BOD. For the lighting portion, it was we use 0.65 watts per square foot for all spaces. Again, it was taken from BOD. Plug loads was defined in the BOD. The electrical and IDF rooms were taken based on mechanical schedules. Occupancy, overall building occupancy, we took all of this data using from the mechanical schedules. The outside ventilation rates, and the number of people were provided on that schedule, and that helped us guide through the occupancy. Outside air was based on California Tile 24. Certain omissions, we did not include this in the model, only to make sure that it's for the sake of simplicity, right? It's easier to not have too many controls, so you don't understand what's exactly happening in the model. So we did not include daylight harvesting, dimming, or any shut-off controls. And we know that it is required by California Tile 24, but for the sake of simplicity and to understand how exactly the model is performing, we omitted those assumptions, omitted those ECMs from our model. Again, same with the receptacle. Any receptacle control that was used in the building is not included in the model. So the Kaiser recommended us to use 250 square foot per person for the overall building occupancy. This is a great assumption. However, while we were because we were also doing system sizing and the annual simulation, some of it resulted in exam rooms having like 0.2 people in that room or 0.3, which we felt it was very low for sizing purposes. Hence, we had to use the occupancy that was based on mechanical schedules. Lastly, the system controls, any temperature, we did assume economizer and basic control, but any other than that, any temperature resets, or if there was any other controls that was part of BMS was not included in the energy model. Slide here. So what we learned in terms of, and we have some recommendations. So this is a snippet you see from the BOD. Occupancy is consistent with Kaiser MOB proof of concept. This was the only thing that was there in the BOD in terms of occupancy. So we would recommend to specify occupancy for different space types in BOD, especially hospitals type spaces, exam rooms or pharmacy or nurse station, those kind of spaces, because generally when an energy modeler sees those kind of spaces, they kind of go towards ASHRAE 170 or, generally how the exam rooms would perform and end up in a higher loads. If that is not the case, having specifying occupancy in the BOD would be helpful. Specifying electrical and IDF rooms in BOD would be definitely helpful, as these are the high cooling load driving areas. And if it's not specified, generally people tend to assume higher loads, and hence overall energy consumption might go up. So this is one other thing we saw in BOD regarding the glazing U value. Like I mentioned before, the BOD provides center of glass U value. It might be mistakenly used for energy modelers. So we recommend to specify assembly thermal performance values for right sizing your peak cooling load. Lastly, The 0.65 watts per square foot that was provided for all lighting, for all spaces for lighting is great. And an additional suggestion or recommendation is use the previous design that was built recently as a basis of design for lighting. As the code progresses, the lighting power densities generally comes down, and it's good to have that data taken from the recent MOV. I'm going to go to the next slide. Ting will talk about how we achieve schedules.
All right. So this part is about how we modify our schedule inputted in the engine model. The schedule assumption in the BOD file is based on a very typical medical office building, but we all know every building might perform a little bit differently. So to make sure the schedule we used are close to the building actual operation conditions as much as possible, we collect the assumption from the different resources. First, based off design file, and then we also reach the Google Map. And then we use these two charts to compare against our actual data. The problem is the actual data, BMS cannot provide it how much people, how much lighting on in the room directly from plan for us. But luckily we have the BMS cooling load profile based on the BMS airflow and air temperature data, just like Peter explained previously. And this trend of the cooling load should match with how the internal heat gain vary with the time. So if we can, also we need to keep in mind that we need to exclude the envelope impact. So we pick an internal exam room as the highlight. We can see the highlight room in the second, in the chart on your right. That room has both typical internal heat gain and also no envelope. So we use this room as an example to study our schedule data. Okay, so next chart. We will talk about the calculated schedule based on the BMS cooling load. Showing in the table on your left, it shows how we convert the cooling load into the internal heat gain schedule. We assume the peak cooling load value is the 90% schedule, and then the lowest cooling load matches the 15% schedule. Then we scale the whole day cooling load to the schedule data. You probably will notice there's two sets of data schedule here. In second set, we only started the data in summertime. Of course, we want to include as much as possible data, larger sample size, but we also need to verify the data whether it's correct before we use it. So we need to make sure the summer and the winter data is consistent. So we can tell we do exclude the envelope impact. So from the chart on the right, we can see there's more and more people before 9 a.m. and people leave by turns around the noon time for lunch break, and they start to come back around 1 p.m., which is in a reasonable range. All right, so next chart, we will compare all four sets of data we talked before. We can see how all these curves go up and down. They match well with each other. We do see the Google data, which is the yellow one. It's a little bit lower than other three. It might be because the Google Map only takes the patient into consideration. So we think it's acceptable. And then we see summer only data and the yearly data, which is the red and green one. They match well with each other too. So it gives us confidence to use the yearly data. So in the end, we use the schedule we calculated from the yearly cooling load as the energy model input. Okay, that's all. Basically, that's all how we modify our schedule assumption with the actual data. Hashana will take over. Yep.
Thanks, Ting. So as Ting mentioned, this was our assumption. So we used this one diversity schedule that we came up with for all our space types and for all lighting equipment and people. So other assumptions we made for the energy model was exam rooms. We treated them as office space. So here in the table, you can see the comparison between the exam rooms and the office rooms. Generally, the plug loads and lighting, if it is not specified or mentioned anywhere, we tend to go with the default watts per square foot, either from ASHRAE suggestions or from like what we've been using from the past so many years, right? So that would be generally like 1.5 watts per square foot if it was an exam room. In an office room, again, since this was provided from BOD, but otherwise also office, generally we assume 0.75 watts per square foot for plug loads. And lighting probably like 0.5 watts per square foot. And especially the thing that makes an impact is the outside air. So exam rooms, you probably need to, if it was exactly modeled as an exam room, we required to do with 2 ACH outside air and 4 air changes supply air. So since we consider this as an office space, we just used it based on California Title 24, which is greater of 15 CFM per person or 0.15 CFM per square foot. This reduced our cooling load to a very low value. We also recommend to see other hospital spaces, like treatment procedure rooms, which has very high outside air and supply air change requirements, pharmacy, nurse station, imaging. It's hard to have exact, the loads for all of these room type, but making, either based on the previous project or making the best judgment on how it will be used. Will it be actually used in a hospital setting with very heavy process loads or just as a MOB without process loads? Making best judgment on these space types will definitely fine tune your model and provide you better results. Okay, moving on. The other thing we omitted was any rooms with supplemental cooling. So IDF, MDF, and electrical rooms in this project had primary air supply from the air handling unit, but also had supplemental cooling using DX, small package systems. So it was hard to understand why our building load was so high. Hence, we removed them from, the any rooms with supplemental cooling was removed. And you can see in this graph, the first one is with supplemental cooling. The loads are higher and the peak is higher as well. And as we remove the supplemental cooling, the yellow line shows and your peak is getting reduced. And this curve actually aligns more with our BMS data compared to this curve. Okay. So based on all these assumptions, we performed our energy analysis, and this is the results. Jessica already explained earlier. This is the same graph. So on the left side, you can see the actual data from the BMS, and the right side, you can see the energy model results. We call it 100% diversity, where this is exactly how we model using the BOD and with all the assumptions we just mentioned previously. So you see the red line comparing the peak of the actual data, and that lines fall somewhere at the 75, 80th percentile, I would say, of the R graphs, which is, so we have some loads that are higher. So hence, we started to look at diversity. So we applied diversity for lighting, people, and equipment in every 10% increments from 100% to 50%. So again, on the green is all the actual data and blue is the energy model data. So you start looking at the line here. So the 100% is slightly over the line. 90% is starting to come down. 80% again, 70%. Well, moving on to the next slide, the 60% and finally the 50% align very closely with the BMS data, how the building is operating. And hence our recommendation is to use 60 to 70% diversity, not exactly 50%, because of, unknown situation that might occur. And also, given the temperature is rising and for the future temperature changes, it's advisable to go with 60 to 70% diversity. Okay, moving on. Some of the QA QC things we wanted to do in order to make sure, our model we built is closer to the BMS data, or, in terms of sizing, operation, and so on. Firstly, we are looking at the zone level peak sizing data here. The left side shows the actual room sizing from the actual data, and energy model data on the right side. And as you see, the line we drew at the 80th percentile of this energy model and followed across to the actual data. Same thing for the exam room. It started here and we followed across. I mean, it's not exactly matching, and that's what we expect, right? The energy model and the actual data in terms of sizing and everything doesn't exactly match, but what we wanted to check here is the scale or the range of these numbers. Do they fall in the same category or not? I think it's reasonable. There are some higher outliners in the actual data, but I think it's not too off. It more or less falls in the same range. Okay. Next thing we wanted to check is, since we based all our loads and the assumptions and the schedules based on cooling profile, so we wanted to check how our model is operating, especially in the cooling months, May to October. The first set of data, we are comparing actual data with 100% diversity. And the second one, we are comparing with 50% diversity on the energy model. As you can see, on the 100% diversity, obviously, I mean, our loads were higher, like we saw before. On the 50% diversity, I think our loads match very closely, even the profile. So we were confident that the model is at least mimicking how the building is operating. The next QA QC was to see how many number of hours fall under which bins, right? How the building is operating for the whole year from 8 a.m. to 6 p.m. So on the left side, the actual data suggests that our building is operating under very low load for most of the hours. So energy model does show the same thing, and then the rest of the number of bins also suggests that on the higher loads we are operating very less hours, and for the lower load we are operating more number of hours. And again, what we wanted to show here is the curve is the same between the actual data and the energy model data. Lastly, we did talk about so many things, so we want to summarize. Assumptions. One, diversity was assumed for people, lighting, and equipment for all space types. Secondly, we assumed exam rooms were same as exam rooms as if it operates as an office space. This would help to lower your cooling load, especially reduction in internal gains and ventilation. Lastly, omit rooms with any supplemental cooling, segregating the IDF rooms and the MDF rooms to two different systems would that's what we assumed in the model. And our recommendation is occupancy loads to be based on either measured data or specifying occupancy values in BOD would definitely help mimic the energy model closer to how it will operate. Design process loads to be served by separate system. These are the same process loads, IDF room, MDF room, or any other process rooms. Having these rooms served by different system than the main air handling unit will definitely help fine tuning. And also it's clear to see to make any tweaks or to understand where we are, the building is operating on higher conditions. Lastly, based on this study, we recommend to use 60 to 70% diversity on internal gains. As Jessica mentioned before, 50% is where we see our buildings are operating. However, due to unforeseen conditions and also a little bit of safety factor, we recommend to apply or consider 60 to 70% diversity on internal gains. Eli will talk about the zone level analysis.
Okay, so thank you, Harshana. This is, as Jess mentioned at the beginning, our version of Table 2 for our this round of studies of medical office buildings. And so on the left, we've got all the different zone types. We've got total zone sample sizes, and we've got the 3 MOBs that we ended up looking at for our different zone types. So we've got Berkeley, Hesperia, and Riverside Kirby. And they all had, different values of different types of zones. So all kind of strengths and weaknesses for each of them. But if we combine them up, we ended up looking at zone types that we had at least 5 total zones across the 3 of them. And then as we go across, we're looking at different exceedance values. So for example, office buildings combined between the 3 MOBs, that 50% exceedance value, there's half the time our sensible cooling load was below that 4.2, and the other half the time it was above it. And if we go all the way to the right, that 0.4% exceedance in the extremes, 99.6% of our values were below that 37.6. And so if we up to the next slide real quick, we've got the same thing kind of showing here for just Hesperia for our case study MOB. And we've got the same value shown above in the chart as well. And so as Harshana mentioned, one of our assumptions was that office zones and exam rooms kind of performed similarly. And this is kind of the basis for that. If we at the first 3 or 4 values, so without all of the extremes, most of the time the offices and exam rooms are closely following each other in performance and sensible cooling load. And the same is reflected in the box and Worcester plots above. You can see a lot more outliers happening in office zone rooms, but the bulk of it, most of the time, the sensible cooling load was kind of very close between the offices and the exam rooms. And so I'm going to pass it back to Jess real quick to wrap everything up.
Thanks. Let's see. Krishan, thank you. So if we go to the next slide, we always leave these projects inspired and having other ideas of things we could do. So one of those, as I mentioned earlier, is perform this analysis on buildings with similar system types, so we can expand our sample size and see if the same thing happens. Additionally, perform this analysis on buildings with different system types. Hesperia had a DX unit, so it'd be great to look at a building that uses chillers and boilers. Next, BIM standards. So at Smith Group, we have utilize the data to create air handling unit zoning plans and also just the individual zoning plans. So having those just required as part of the documentation, we see that as a huge help in making the data extraction process much easier. And with that, with the data being live within the building information model, you can require a schedule that can be easily extracted with all the information that's listed below that we use to get our data to be able to be analyzed for this process. And then next, some other ways we can use this data is for retro-commissioning for energy saving measures and operational improvement, and be more proactive and able to really dial in on what you need to evaluate. So seeing some of the third point, additional quality control investigation into the outliers in our data analysis, we saw, why is cooling happening at like 3 a.m. really heavily? So we can look at that and see, is there a sensor that's not working? We were missing outside air data. What's going on with that? So having this analysis be part of the process could help your building perform better and save energy. Exploring the digital twin. So it would be great to be able to have more confidence in our energy models, being able to model a potential energy measure and feel confident in making a decision with moving forward instead of being unsure with trying something new. And lastly, sharing our findings with the California Energy Commission, making an impact beyond just Kaiser would be a great way to move forward. And for more inspiration, there's other studies we could see using this data for, like looking at domestic hot water demand profiles and developing heat pump and storage sizing criteria. Also looking at a full system review of different specialty rooms. One that comes to mind is medical equipment room cooling load diversities. A lot of the equipment rooms housing the equipment for Linux, DTs, hybrid ORs, etc., they have a high heat gain, and often facilities and the manufacturers don't feel comfortable giving a diversity. So we'll, as the engineer, do that 80% diversity because it feels safer. But if we have actual data, we could make a more informed decision. So that's just some of the ideas that we have. And I think that that concludes our presentation. We just thank you for letting us be a part of this. We really enjoyed it, and I think we learned so much, and hopefully this will make a big impact to your basis of design.
Okay, we're at 49 minutes, but I think we should keep going into some Q&A. Absolutely, this is thanks a bunch. This is great work. I know that it'll have a big impact in our basis of design. We normally see our engineers when they do load calculations for clinics, they do no diversity or 100% diversity, and then they add a 10% safety factor on top of that. And I think what I heard you guys saying pretty clear is that even with safety factors, you should be at 60 or 70%. And so I'm sure we just need to figure out how to roll this into our BODs. But let's start. I wanted to open for questions, and this may sound odd, but I'll start with questions amongst the Smith Group team. Do you all have any softball questions for each other, or something that you wanted to see said differently? Or
I think just one thing from my perspective is that the study was really eye-opening, but it would also be helpful to have that higher sample size to have more confidence in what we are seeing. And if there's anything more specific, I'm sure Peter and Eli would, as the data scientists, probably agree that it might be helpful.
Yeah, I agree with that. Always more data, right? And then there was really only one facility that we compared the actual to the modeled data as well, to Jessica's point. But yeah, I mean, there's, I don't know if I have any more questions for my colleagues at Smith Group. Just an appetite for more. I'll come back to like that Clockworks API is just amazing, the amount of data that is there already for all the Kaiser facilities. It's like a treasure trove.
I'd just like to I guess tack on to what Peter said, that yeah, we really did just match the energy model to what we found with Hesperian. So it'd be great to I guess kind of continue the process with some other MOBs and see if we can hone that number in a little bit closer and try to get similar results.
Also, me being from the East Coast, would love to try a different climate zone and see some of the other impacts of the different system types that are over here more predominantly.
right.
I had one question, I mean, just in general for all of you. So we work on many, so I help with load calculations as well as I also do the modeling exercise. So on the load calculation side, I see that the most discrepancy is especially for heating side in the energy modeling. I don't know if Travis, you probably see the same thing from your group or not. Energy model is actually kind of undersized for heating, and sometimes it's like, so is there a heating data, Peter or Eli, to analyze? I mean, that is something I really want to learn more, or how the actual building performs in terms of heating.
Yeah, and that, well, I can talk about with my limited knowledge of how HVAC systems work, but we basically filtered all that out. And that's something that we looked at with the acute care facilities. And we did see some oscillations between heating modes and cooling modes. So that was mitigated somewhat by aggregating to the hourly level. But we still just, even besides looking at the air handlers to remove that, looking at the individual zone level, we just filtered out whenever there was a heating load for that 5-minute increment. So we only looked at the cooling loads, but the data does exist there. I don't know whether that makes sense or we need to augment it with other inputs.
And I think that's where also looking at other climate zones, like me designing around New Jersey and Boston, we have to oversize the heating per code. So it might be more interesting or for looking at data for a different climate zone for some of the heating, though still valuable on the West Coast.
It also somewhat relates to one of the next steps that Jess mentioned, with looking into source of some of the outliers. I remember with the acute care facilities, part of the reason that we kind of strayed away from the heating was that some of the at least from an individual zone standpoint, some of the hours that had the most heating were in like the middle of the night in February, and so it kind of got to the point where we weren't really sure if we wanted to trust some of that data, and so we kind of stuck to cooling in the summer, at least going back to the acute care facilities.
Right.
Makes sense.
Travis, I had sorry, Pierre, did you want to go?
I was just gonna make an observation too, like I thought it aligned really well. Like the whole thing for me was like we have actual data and we have modeled data, and what's going to happen when we bring them together. And I think initially when we first started this project, I was a little skeptical, and I probably would have lost any bets that we would have placed there. Especially once adjusting for diversity, I was really pretty impressed with how well the energy model aligned with the actual load data that we calculated.
Yeah, I think I appreciated our approach of keeping it simple because you can get really deep into it. So I think that's really key in some of these analysis that we do, because if you start too detailed, it's just rather start simple and then figure out if you have to go more details. I think that's really key. But Travis, I had a question for you. So I have a very extensive BIM background. So do you see Kaiser thinking about adopting some BIM standards to help make a study like this more easy in the future? Because I think a lot of our time is in the data processing. If the data was there in the format we needed it, we could have done a lot more. So that's where in the beginning where we whittled it down to just Hesperia because of data being an issue and time. Do you see BIM standards also, and also the BMS? But I think I heard that that's being implemented already.
That's a good question. I don't know. We can kind of follow up with our contracting team that's working on this particular thread of medical office buildings. And I remember discreetly the conversation that you're talking about. If we could have within the BIM model, the zone number that then matches the zone number that actually shows up on the BAS, so that when we pull data for zone 1-033, that we already know the area and we already know the room types that are in zone -1-33, and therefore we can do really quick comparisons of the data within the zone. So that's definitely something we can follow up on between the controls designers and the actual BIM implementation team, for sure.
Yeah, I think it's helpful because as an HVAC engineer, you have the Title 24 documents, but if the zoning plans aren't included in the documentation, right, when we're doing it, we're like, well, we think this is the part of the corridor that's in that zone that's serving from the nurse station, and we kind of just guess, and it takes time, but it's really easy to do if you're doing it while you're in Revit. So right. I think Canon had some of those in their plan. So, and Smith Group does it. So having that as a standard would be huge.
Yeah, I will say, yeah, that's actually kind of, believe it or not, that's actually improved. I think 5 years ago when we started looking at some of this stuff, you would have a set of load calculations, ventilation calculations, and then a set of plans, and then controls drawings, and in between those there'd be 5 different sets of zone numbers on it. So it'd just be a complete mess to look at. And so but yeah, the point taken for sure. Let me ask, I see Glenn and Ben and Sandy are online. Did any specific questions from you guys on this work?
This is Ben. I was wondering, since we concentrated loads to study on MOB, could we apply the diversity recommendation to hospitals?
No, there's actually another team working on, so there's another video that we recorded last week with the hospital team, the San Jose hospital team. So very similar study. in terms of trying to true up the hospital stuff. So they did specifically patient rooms and operating rooms and PACUs and stuff like that. So we have that. So between this study, where we kind of now have what I would say is a reasonable design load profile for clinic spaces, and some diversity recommendations on that. And then the other study, we actually have a pretty good design load profile for the hospital spaces. So I think we actually kind of have a first pass at both of those. And I guess what I would point out both to this team and the other team and anyone else is that I think it was Glenn Kuramoto that told me, you'll never have the data that you want, and you'll never have enough data, and you'll always want more data. But we didn't learn about the universe by wishing we could see the other side of the stars. We learned about the universe by seeing what we can see and then learning as much as we possibly can from the data that we have. And in that sense, this study and the results of this study are infinitely better than anything we were doing prior to somebody having done this type of true-up study. And so I think I'm not going to hesitate at all to implement this as a standard sort of moving forward in 2023. And I hope that somebody breaks it in 2024 and 2025 and we get something better. But I'm very positive this is better than what we have to date. Any other sort of questions or closing comments? We're at an hour, so if nobody has anything else pressing, then I will stop the recording.
I think I'll have to watch the recording, Travis. I was on 2 other meetings at the same time. The big thing I wanted to know is, did we validate the kind of the loads that you had published before, like cooling loads 20 BTUs a square foot, heating 10 BTUs a square foot?
Yeah, actually, I wrote that down. Eli actually had 2 slides in here, slide 41 and 42, that are some really good updates to that sort of famous table that we published out of the last study. And so actually the one before this, Eli, was the one that, if I'm understanding this correctly, this is basically an update or more entries into the table 2 that we published in the paper last year, right?
Yeah, exactly.
This is essentially the same style of table.
Yep.
Same numbers. Those exceedance numbers are all the same as what exists from last year. The zone types might be different because we're looking at a different type of facility, but otherwise, yeah, this is our, I guess, table 2 version 2.
Right.
Right.
See, that's
right.
that's by zone. What we're looking at sometimes is overall building.
And that was very much what we saw during the load and energy modeling phase. So yes, absolutely, we sort of have that in the deck.
Good. Thanks.
Okay, well, thanks everyone. I'm going to just press stop on the tape. Nobody has to leave the call right now. In fact, I think I want to stay on, but we will stop the recording right now.